Hello friends, till last lecture we have seen the basic concepts of infinite series. Some of the topics we have completed like as the partial sum, integral test, P series, comparison test and ratio test. Today we are going to start with a root test and Limelist test. So these are the two topics today we are going to discuss out. First one is a Cauchy's root test and second one is a Leibniz test for alternating series. Now, first starting with a Cauchy's root test. Suppose sigma un, where n is running from 1 to infinite, is a positive term series, and if the nth root of un, that is un raised to 1 upon n, has a limit L, then for 0 less than L less than 1 series converges, for capital L greater than 1 series diverges, and for L is equal to 1 test fails. Okay, that means you have to apply some another test. Okay, these are the conditions same as a D'Alembert's ratio test. Now, if un is of the form vn raised to n, that means something raised to n you have, in that case, or some power of n in power, then we are going to apply the Cauchy's root test. Going with the example, test the convergence of sigma n running from 2 to infinity 1 upon log n raised to n. Okay, so here see, your un is nothing but 1 upon log n raised to n. Now log n raised to n is given, that means whole raised to n form you have, that means you can apply the root test. So we are starting with un raised to 1 upon n, that means nth root of un, that is nothing but 1 upon log n. Now applying limit to nth root, that means limit n tends to infinity un raised to 1 upon n, then it will be a limit n tends to infinity 1 upon log n. And if you are going to apply the limit, then 1 upon log infinity, but log infinity has a value infinity, so 1 upon infinity will be 0, and this value is less than 1. So by your Cauchy's root test, this series is convergent. Now we are going with one another example. Is the series sigma n e raised to n convergent? Question mark. See here, this series can you can discuss the convergence of this series by integral test also, by comparison test also, and you can also apply the ratios test. But integral test is not applicable because this is not a decreasing function. But you can apply comparison as well as ratio test. But here we are starting with the root test. That means any series can be solved by more than one test. Okay, so you can discuss the convergence with more than one test. So please remember, it is not necessary to apply some particular test. It is your conveniency. Whatever you have to apply it, and if the result is there, then you can say that whether it is convergent or it is divergent. So here we are starting with un is equal to n e raised to n. So taking nth root both sides, that will give you un raised to 1 upon n is n e raised to n whole raised to 1 upon n. If you are going to apply limit, then you will have limit n tends to infinity un is equal to limit n tends to infinity nth root of n into e, correct? Separating 1 upon n, and e is constant, so e common out, and we are already aware of nth root of n has a value 1. So you have the limit e, that means whatever the limit, e is 2.71 something, which is greater than 1, and since it is greater than 1, so your series is divergent by root test. One another example we are going to check out. Test the convergence of 1 cube upon 3, 2 cube upon 3 square, 3 cube upon 3 cube, 4 cube upon 3 raised to 4, and so on. That means here see, in numerator you have 1 cube, 2 cube, 3 cube, 4 cube, and so on. In denominator you have 3, 3 square, 3 cube, 3 raised to 4, and so on. So in numerator you have n cube, and in denominator you have 3 raised to n. So here also you can apply the ratio test, but here we are going to apply the root test. So un raised to 1 upon n is equal to n cube upon 3 raised to n whole raised to 1 upon n. So if applying limit and separating the numerator and denominator, that will give you n raised to 3 by n divided by 3. Now we are writing n raised to 3 by n in the form of nth root of n whole cube, because we are aware of limit of nth root of n. Now nth root of n, where n tends to infinity, has a value 1, so it will be a 1 cube divided by 3, so that will be 1 by 3, which is less than 1, and therefore your series is convergent by root test. Now we are going with is a alternating series. Now this is the particular type of series which we are going to check out, and for that one particular test is applicable, which is a Leibnitz test. A series is called alternating series if its terms are alternatively positive and negative. That means one is positive, then second is negative, third is positive, fourth is negative, and continuing this way. So if you are starting with a positive alternating series, then terms are alternatively positive and negative. And the only test we have is a Leibniz test. For a Leibniz test, suppose sigma minus 1 raised to n minus 1 into un. That means u1 minus u2 plus u3 minus u4 and so on, where un is greater than 0. That means we are separating the power of minus separately, and then the remaining term is a positive term. So if this series satisfies two conditions, un plus 1 is less than un for every n, and if the limit of un is 0, then this series is going to be convergent. That means you have to check out two conditions. First one, the series is numerically decreasing. That means without sign plus or minus, it must be decreasing. And secondly, the limit of nth term without sign is 0. You can also consider it with sign or without sign. Okay. So we are going to check out one example. Test the convergence of a series sigma minus 1 raised to n plus 1 divided by log of n plus 1, where n is running from 1 to infinite. Now your un is 1 upon log of n plus 1, because we have an alternating series, so power of minus is neglected. Only the positive term part is 1 upon log of n plus 1, correct? Now we are already aware of log is an increasing function. So you have log of n plus 1 is less than log of n plus 2. And if you are going to inverse them, then inequality is going to be changed out. That will give you 1 upon log of n plus 1 is greater than 1 upon n log of n plus 2. That means this is left hand is your un, right hand is your un plus 1. So un is greater than un plus 1. The first condition is proved. Same manner, second condition is limit n tends to infinity un. That is equal to limit n tends to infinity 1 upon log of n plus 1. But log infinity has a value infinity. So you have 1 upon infinity, and therefore it is 0. So both conditions, the series is numerically decreasing and the limit of nth term is 0. Both are satisfied. Therefore your series is convergent by Leibniz test. Now test the convergence of a series 1 minus 1 upon 2 root 2 plus 1 upon 3 root 3 minus 1 upon 4 root 4 and so on, so on, so on. Here you have un, if you are writing it in a sigma form, then you have minus 1 raised to n minus 1 into 1 upon nth root of n. So if we are writing un without sign, then un will be 1 upon nth root of n, n into root n. So un will be 1 upon n plus 1 into root of n plus 1. Again we have to prove this series is numerically decreasing. For that we are starting with an inequality. N root n is obviously less than n plus 1 under root n plus 1, correct? So if you are taking a reciprocal, then you will have 1 upon n into root n is greater than 1 upon n plus 1 into root of n plus 1. So left hand side is your un, right hand side is your un plus 1, and that's why this series is numerically decreasing without sign. Now the limit of un. So if you are applying limit to the un, then you will have 1 upon nth root of n and n into root n, where n tends to infinity, so 1 upon infinity will be 0. So both conditions are satisfied of Leibniz test. Therefore by Leibniz test, this alternating series is convergent. Okay. Now we are going to check out the summary. See, we have learned 5 tests for positive term series and 1 test for alternating series. See, it is not necessary that each test is applicable to each series. So we are going to short out it. See, if your series is of the form sigma 1 upon n raised to p, then directly p series is applicable, and we are already aware of the p series converges for p greater than 1 and diverges for p less or equal to 1. Same manner if the given series is a geometric series with ratio r, that means if it is of the form sigma a into r raised to n minus 1 or sigma a into r raised to n, then in that case we are also aware of geometric series converges for mod r less than 1 and diverges for mod r greater or equal to 1. Now, if you can see that the limit of nth term is non-zero, if the limit of nth term, by seeing un, you can directly check out whether the limit of un is 0 or not. So if it is non-zero, then by test of divergence, you can tell that the series is divergent. Now, same manner we are going with a comparison test. For the comparison test, we are going to use the geometric series or the p series, correct? In particular, if you have given any rational function, which is the algebraic, that means numerical part is algebraic form, in the denominator part is also in algebraic form, involving the polynomial as well as any power of n, then we are starting with a generally p series and we are going to use the comparison test. And how to find out the value of p, that we have already discussed. You have to take a dominant part from numerator, dominant part from denominator, and then we are going to calculate what are the values of p. Now, if the series is of the form sigma minus 1 raised to n into un, that means it is alternating series. So there is only one test for alternating series, that is nothing but it is a Limelist test. Same manner, if the series contain the factorial or some powers of constants or some multiplications of constant, then the ratio test is applicable. And something raised to n is there, then the root test is applicable. And the condition of both of them are same. And the last one is, if un is equal to fx, that means your function is going to satisfy the condition of integral test and integration is possible. In that case only we are going to apply the integral test. Okay, so these are the topics and we have learned for infinite series. If you have any query or any doubt regarding this topic, then please feel free to contact me. Thank you.